So, und dann machen wir weiter. Ich kriege gerade den Hinweis, dass wir weitermachen können, weil unser nächster Redner nämlich schon da ist. Professor Sami Haddadin vom Munich Institute of Robotics. Muss man eigentlich nicht mehr viel großartig ankündigen. Koryphäe beim Thema Robotics, zahlreiche Veröffentlichungen, Vorträge etc. Und ich bin jetzt sehr gespannt darauf. Sein Thema ist The Next Wave of Robotics, from Collaborative to Tactile Robotic. Ja, ich bin sehr gespannt und ich glaube, die Bühne ist bereitet und Sie können loslegen.
Danke. Ja, super. Vielen Dank für die Einführung. Jetzt schauen wir, ob es auch wirklich so weit ist, dass ich anfangen kann. Alles klar, wunderbar. Ja, also, ich bin mir gar nicht sicher, auf Englisch oder auf Deutsch? Wie ich mag, ne? Ja, dann mache ich es auf Deutsch, ist heute einfacher. Gestern war ja lange Standparty bei Fanuk, oder? Waren ja sicherlich viele. Wunderbar, also, gestern um 17 Uhr ist meine Stimme schon quasi niedergegangen, deswegen hoffe ich, dass man mich heute halbwegs noch versteht. Aber ich sehe, es sind ein paar Internationale dabei, deswegen switche ich doch to English. So it's great to be here, great that we have automatica again, great that to see so many familiar faces, great pleasure to see 3D again, not 2D anymore. We all exist, we all collaborate, and we all can come together to push robotics forward again, which I believe is really fantastic. So I kind of have a little bit of a bold title because I think it's important that we as robotics community kind of make clear that we are entering a new phase of robots, and I think it's extremely interesting to see that we have, come from some of the greatest, I think, pioneers in the field: Hirzinger, Siciliano, Asfur, Thorsten, and Aline. We came to Automatica. This was on Tuesday, I guess, and we directly came together and found each other. So what was super interesting about that it characterizes also some of the people who really pushed robotics forward. And all the ideas you see about cobots, about interaction between humans and robots, and force sensing, and all these kind of things, kind of were conceptualized and pioneered by these people. And I had the pleasure to, see them again, which was really fantastic after so much time. But at the same time, what I believe is different at this Automatica is that we are not anymore in the classical phase of robotics. I have the feeling, and I guess all of you have the shared experience as well, that this Automatica is kind of special because it's all about people interacting with various kinds of robots. So we're not anymore in the year 1999 or 2000 when I was at my first Hannover Messe. I'm actually originally from Hanover, so this is where you go typically, and you see robots, and the only thing you hear is like zzz, 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 right? So now we have robots that really interact with the world in a kind of interesting way, in various forms. I mean, running, jumping, flying. We can see robots directly controlled over the internet in the US right now at our AI.Society stand and before, and it's really showing tremendous progress in robotics, not only in the research field, but now really in translation, in new startups. So there's this new innovation of startups. So all these kind of things have been happening, which I think is really fantastic here at Automatica that we can see that. And this can really be kind of a kickstart for the future of various revolutions we will see over the next years. So, but let's come back to the actual kind of content of my talk. So I was trying to kind of convey a message saying that, well, I mean, there has been this idea of humans and robots interacting with each other. My own PhD thesis was actually denoted towards safe robots, approaching Asimov's first law. And many of the things we've been doing back then, still at my time at DLR, with Hirzinger and Aline, were basically laying the foundations for what we call today cobots, right? Collaborative robots, meaning basically that you can take safety fences away, humans and robots coexisting in the same space, right? So that's one thing. But now more and more we can see also, if you see new robots coming everywhere, that people more and more acknowledge that it's not only about interaction, but it's actually about interaction with the world, not only with the human, in the sense of that the task that the robot is supposed to do is very different. So we move more and more into this idea of translating the sensomotoric behaviors of the humans into robots, meaning purposeful, force-sensitive interaction with the world, meaning manipulation, meaning applications in assembly, and so on and so forth. If we look at one of the largest growing sectors, logistics and robotics, then we also can see that beyond mobility, beyond all the automation in the warehouses, we can see now more and more this idea that we need sensitive interaction with the world, manipulation, grasping, and the idea to really have flexible helpers that can automate manipulation processes. And there has been a big technology jump over the last decades, you must say. It was not really very fast. It was a continuous, long-term disruption, I would say. But finally, we are not anymore in the phase where, I mean, you all know this. I always like to show this picture because Jan Böhmermann is always, he had a show where he copied my picture basically, so I have to keep it in my talk. And he was kind of not getting the actual content of the slide, meaning that we have been revolutionized and run out of jobs in 1964 by robots, 1978 by robots, 2016 by robots, and I think we all know this has not happened. So there seems to be something different about robotics. So there has always been this myth that we, roboticists build machines that steal jobs. And I think it's very clear that robotics, especially this new age of robots, is doing a very different thing. So we're having more the idea that instead of having the classical automation in the 2000s with humans being isolated, not being part of the machine world, now we kind of tear down the safety fences more and more. Obviously, it's not going as fast as we all hoped, but there is many things you could now criticize about standards and so on, and we all know that they are extremely conservative. There's also things that are not really how they should be, but I guess there's a lot of will to push that forward. And more collaboration, so cobots can become in existence, but in the end, what uses it for if a cobot is not doing something new? So what is this new thing? And if you look at the industrial robotics chain of over the last century almost, starting from Gargantula, then going into the industrial robotics generation, the first generation of position-controlled machines, and obviously I have left out a lot of robots, right? So please don't be offended if I missed your robot. It's really just trying to make a point, because I think we all as a robotics community kind of have now an interesting point in time, meaning we have the second generation, which we call cobots, so robots potentially interacting with humans, but still doing the same thing as before behind fences, and now having robots that really have a sense of touch. Not necessarily, human kind or human-inspired sensing, but the interaction with the world in terms of forces, in terms of, manipulation processes, understanding how to contact the world, understanding how to manipulate the world, and understanding basically how to, purposefully do the things that we as humans make so elegantly and so easily. And this third generation of robots is what I call tactile robots. So it's not just anymore about building a system. No, it's about the software. So the new robots are much more than cobots, about 80% minimum software. So it's all about software now. So you have new sensors, but then you need this new central nervous system that becomes the largest part of the robot developments. So truly embedded AI systems. And obviously there have been many key influences in tactile robotics, so ranging from the force control in the 80s and the unification into force impedance control about 10 years ago by us, torque control dynamics of Chris Atkinson and John Hollerbach. So all the famous people in robotics in the 80s and 90s and 2000 and also in 2010 have really contributed to this enormous kind of journey, such as Antonio Bicchi, who just gave a marvelous keynote at the first ICRA we had again in Philadelphia just a few weeks ago, or Alessandro De Luca, Mark Spong, so you name it. All the really amazing and fantastic people who have pushed the field, and they were always dreaming not about position-controlled machines or cobots, no, it was about robots interacting purposefully with the world. And obviously safety is a big topic on that, but since I see that Björn Matthias is also here, we're going to have a discussion about the current safety aspects, maybe later on, so I don't talk so much about this today, because I think it's really about what can we do with these machines. And what I think is kind of interesting is that if you boil it down to one thing, I mean, classical position-controlled machines. There's some experiments which I did when I was still a student at DLR. So I had a lot of fun of crashing things into, things. Lots of fun if you're there. You cannot convey the message so nice if you just see a small video, but if you're there and a 2.5-ton robot crashes into a dummy, and it's an interesting image and video that you don't lose over the years. Then you have the collaborative robots, which obviously have safety fences removed, but in the end, obviously it's not about tactility, it's about only safety. So they cannot detect the contact yet beyond certain, severity. And then comes this last generation of tactile robots with the sense of touch and the reaction, the central nervous system that can, make sense out of force information. So it's not only about having a sensor, it's making sense out of the sensing, right? So this is, I think, really what we need to do, and doing controlled, purposeful controlled interaction with the world. So as you know, many of us have been contributing to that, and one of the core things that we've been doing as a community, I mean, the idea was born in the late 70s and early 80s, building torque sensors into the joints. So joint torque sensing has been instrumental to that, and these things enable smart teaching at a level that is way beyond current control. But really, you know, it's like feather-like interaction, several hundred grams instead of 17-kilogram motion. So you really have robots that you can take by the hand and you can show them something. And many of the things we've been doing back then at DLR were then, as you know, tech transferred to KUKA. It was about lightweight robot technology, torque sensing, and low-level control. This was the main thing we did back then. And obviously, the safety aspects you see there, so I always say these kind of, you know, original experiments with, I don't know, some PhD students had to put their head in the you know, direction of robots, you know, to show that they are safe. We are still not there that, you know, in the real world, humans can broadly use robots, but I think it's more and more going there. And still, I would argue that we are totally overestimating the danger that is emanating from these super lightweight systems. I mean, obviously, if a 2-ton robot or a more robot with, let's say, 2 or 3 or 4 kilogram reflected inertia, that's a totally different animal, right? So I guess we're still on a road there. And then we have been doing these ideas of torque control, you know, robots that kind of float in space, essentially, right? You compensate for gravity, centrifugal Coriolis terms, and then they become super smooth and very nice to guide. Yeah, and then these things had to be continued into tactility. So this has not been yet tactile robots at all. It's only torque sensing, it's only gravity compensation. So torque itself is not a sense yet. Torque and forces are not yet being controlled in an elegant way. So, and obviously the reaction is still very important. So how do you embed this into the safety cycles? How do you make robots as sensitive that with these kind of needles in the front, you can really detect and react to collisions in a millisecond level? And these things together now with a sense of touch and super stable control methods that make force interaction with the world really purposeful, so that you can, regardless of the interaction material, so whether it's compliant or very rigid, the robot is able to very, very accurately control a contact force. So this is something that we as humans are not even able to do. So this is kind of a superhuman level of force interaction that you could, in principle, do as a robot. So what can we do with these kind of new ways of interacting with the world? And obviously it's not like in a computer game, only position control, so we try to make the robot basically a pure geometric abstraction, but now we can interact purposefully with the environment. So we tell the robot control or contact the environment with, I don't know, 8.2 Newton, and it can do it. Next thing, obviously, of a tactile robot is autonomous learning. So can we really make these robots learn the interaction with the world? Can we make them learn like our kids? So I do all kinds of experiments with my kids. I will not replicate what I've been doing there. So, but I've got 3, so it's kind of nice. You can repetitive patterns there, and these ideas can really be brought into algorithms. And what we've been doing is really to try to fuse human kind of inspired motor control schemes with machine learning to make robots able to solve quite ambitious peg and hold problems with industrial kind of clearances. Very hard to automate that. And the robots are able to learn these things autonomously. And obviously the next question is, can you transfer it? Can you transfer knowledge from one task to another one? And this is an experiment I already showed for some times. And yes, you can do. You can actually use a program you learned before, and just within seconds, the robots are able to autonomously acquire the ability to put the key into the hole. And believe me, if you don't do it with these kind of methods, it's actually quite hard, which I'm going to show you in a second. And then the other thing that obviously has to be brought into attention is this extremely important aspect of making robotics accessible. And not only teaching, but programming should be, I like the idea of this no-code program that was brought up, I think, by Wandelbotz in Dresden, at least as a catchphrase. And I think we introduced 2016 at Hannover Messe, basically the first system that was really able to do that. So can you do this not only with pick and place, but really force sensing with, you know, manufacturing tasks, assembly tasks, and so on and so forth. So there's really the big ambition to have robots being able to do quite complex assembly tasks and then let them be programmed or used by anyone, essentially. So essentially we're trying to build, you know, inspired by the human homunculus, a system that does not only have collaboration, but it has a sense of touch. And this is the homunculus that shows kind of what part of the brain of the cortex is responsible for your bodies. I think it's kind of clear we need a sense of touch. I guess we all agree, right? Otherwise, no manipulation is possible. So this is exactly what we should do in robotics and push much more forward. So the revolution we see here, we could say that, I mean, vision is important, yes, but I think if you see the volume of the hand, it's kind of clear that manipulation really relies on the sense of touch and the central nervous system. And these ideas really could be, you know, used to do all kinds of things that could not be done before. And if you go to before, you see now all kinds of robots, you know, this more and more next evolution of robotics. And I think what is kind of interesting is that many new things are possible. I mean, electronics manufacturing, assembly testing, you name it, and more also other applications we all have seen over the last years. Okay, and then I think what is really interesting is that robotics has kind of surfaced from this, very kind of specialized industrial level machinery into systems that large-scale, corporates are using in order to further progressing in their machine learning world, in AI. So this bridge between machines and machine learning is, I think, really happening now. And that's really where I think this revolution is coming from. Our machines can produce not a lot of data, but high bandwidth data at very high frequencies, right? So we always say that it's very hard to generate data in robotics. Yes, because the robot first needs to be able to do something, and if you don't know yet how it does it, then how do you generate the data to do it? So that's kind of the chicken and egg problem we have there. And I think what is really interesting is that now more and more companies all over the world are using these next generation systems. So at ICRA, if you went there, you have seen that now essentially the community has been converging towards this next level of tactile robots being the reference in robotics research and more also in the industry. Okay, so coming back to what is good for, right? I mean, why would we need a generation 3 and then 4 and 5? What is it good for? I think it's clear that the classical robotics world, and this is obviously not a complete list, but I think it gives an idea of it, has been pick and place, spot welding and painting. Second generation has more and more come to this kind of rough teaching, at least some positions, right? And then machine tending. This has been a great game changer, I think, in robotics. But now with the sense of touch and all these new ideas of robots being these smart assistants and being programmable by anyone, you can really, you are the one who is using a tool. It's not anymore the machine telling you what to do, but you as a programmer, as a user, can essentially have a very interesting toolbox, you could say. It's a smart toolbox. It's not just a hammer, it's an entire set of tools that tries to support you, which I think is an amazing transition that we are seeing in robotics, moving away from classical machines to smart assistants, not anymore in our labs only, but really in the real world, which I think is a big transformation we see at the moment. Yeah, and then I think what is... I think what is really nice is, wait, I actually want to jump over that. Sorry. Is basically that these systems now can be really used for all kinds of things. So obviously what is kind of super interesting is that we do all that stuff in industry, in small and medium enterprises, but I think what is actually really important is that these robots are not only doing all these things, as for, 3C manufacturing, obviously now with the first certified tactile robot being the Franca Amica system, but really the idea of these systems not only being done for one thing, but more and more people use these kind of new robots for things that we as classical industrial, let's say, thinkers or technologists were not thinking of. And obviously this idea of bridging the digital to the physical world, I think, is really one of the most fundamental transformations we've seen in the last years. Obviously, this kind of comes with lots of potential. So why did I say this is a toolbox? Because obviously you have all these purposeful, very sensitive interaction between, and gentle and safe, between humans and robots, the connection to the app world, and so on and so forth. Obviously, safety being a very important aspect. But what I think is really cool is that next to the industrial level certifications and so on and so forth, these enable things that we all couldn't think of. So this movie, for example, has been fully done by a movie maker by using robots, right? So he's teaching these robots and interacting them. So the robots are now basically being a tool for the movie maker to do a movie. I mean, how awesome is that? So, and these things you can see more and more. A Swiss cheese maker is using robots for doing Swiss cheese. A very famous guy in Switzerland, I heard, at Davos, right? So it really comes into the first format role in order to really bring robots to human spaces, and especially to people who are not industrial only. And I think another aspect that we see now, I'm always being asked, so why do you need this only for arms? Could this be useful also for other things? Yes, I think it's useful. So impedances, compliances are not only useful for arms, but actually they will, I'm pretty sure about that. This is something we just published at ICRA, so just a few weeks ago, the first mobile base that is truly tactile. So all these tactile ideas bring it to mobile systems. So there is no bumpers or anything. It's really compliance-based robot systems, active compliance control, impedance control, and also these notions of collision reactions, reflexes. So basically, I guess we all want to have a mobile base that is able to do that, right? So without a bumper, just with internal motor control, torque sensing in the base, torque sensing in the drivetrain. And obviously, if you want to go to human spaces, this should not be happening. So obviously, these systems are very strong, but in the end, we would rather have a system that is able to gently interact with us. So let's also be aware that if you want to have mobile robots in our environment, in human spaces, it's the same thing as for arms, maybe even more important to do that. Okay, so one thing that I guess is really important with this next level transformation in robotics, and why is he kind of talking about cobots and then tactile robots, is to objectify and benchmark this jump, right? So we always talk about position accuracy and repeatability. I mean, in terms of assembly processes, this is not even closest to the most important benchmark, obviously. We want to objectify how do systems purposefully interact with the world. Can we quantify that really objectively? So obviously, if you come from an industrial process that you want to solve, then obviously you want to have a set of automatable tasks, then come with the task and safety requirements, safety today not being the main point of my talk, and then coming into technology specs and the selection of a robotic system, right? So how can we do this in the tactile realm? How can we do this in the teaching realm? Can we actually define and propose, first of all, benchmarks and really tests that quantify the quality of these kind of professions? Similar to position accuracy and repeatability, we need the same thing in collision reactions. We need the same thing in contact, awareness, and especially we talk about trustworthiness and human-robot interaction, trustworthy AI. People care about these things very, very much. So I guess it's clear that these tactile robots are now enabling fundamentally new processes, so we need to be able to objectify what these systems are able to do. So how do we compare these robots? So for example, if you want to have a robot that is able to insert collaborative assembly-wise with transition fits, and let's say the specification says 1 Newton force accuracy and 0.5 Newton repeatability, and safe contact detection with the human. So how do I come up with a robot that is able to fulfill all these specifications would be the fundamental question we ask you. So I seem to have music everywhere. Sorry for that. Yeah, and I think what is important is now that we see more and more of robots, doing, and it's kind of, we call them all cobots, and I think it's not really what's happening here. So we should make sure that we understand that all these systems, they all look like arms, right? I mean, but in the end, they can do very different things. And what are these things that they can do, and what can we do with it? What kind of processes can we transform? So we need to understand how do task requirements, converge into benchmarks, obviously. And what kind of benchmarks are useful to quantify these transitions, especially if you want to go to processes like assembly, if you want to go to processes like insertion. So all the things that could really mean big scaling, especially for us, in times where reshoring, in terms where scaling for small and medium enterprises becomes very important. So we all know position accuracy and repeatability, right? I mean, this is has been in industry for decades and has been standardized. But what happens, with human-robot interaction? What happens with tactility and in manipulation processes? What is the analogy in motion, tactile, and safety performance? Shouldn't we specify and benchmark them as well? Otherwise, you can never choose the right robot for your task, right? So, how do we do that? Something we have been proposing is basically a set of tasks and a set of benchmarks just recently published. So, for objectifying force accuracy, force overshoot. So if you want to grasp something and you just apply a force, but the overshoot is too large, then I think we all have already tried this with eggs, for example. It doesn't bring you the egg back. So one thing is it's broken, so we need to be able to control that. And then obviously the maneuverability. I don't know how about you guys, but if you teach with a robot, there's certain things that can go really well, and sometimes teaching is really hard. So how can this teaching ability be objectified? And then obviously in the safety realm, the constrained collision forces. We all know the TS 15066 and the requirements, so obviously these forces should be objectified and be benchmarked. We need to objectify the contact sensitivity. So given a standardized test of collision, can we actually objectively compare the capability of a robot to react to such a collision? Which obviously manipulation is equally important, because if you want to have a robot interacting with the world, the braking time and braking distance would be important, not only to rate, but actually to quantify and objectify, because in manipulation, it is more than just a safety problem. It's a manipulation problem. So just to give you one example, so contact sensitivity obviously should be objectively independent, rated from the robot itself. So the easiest thing is obviously, if you think, as someone who really likes physics, I think we all like there's mass and velocity, right? That's momentum, that's energy, so everything is fine. So why not just say there is a pendulum with a mass, the robot comes with a velocity, and the question we ask is, given let's say, the environment of the system, can the robot detect a collision and react to it in due time? Very simple, very objective test, nothing there to trick. So, and obviously if you do these tasks and you compare it, then obviously it becomes very clear that we are not anymore in the collaborative robot space, but there is now robots that really have this next generation abilities, which we call tactile robots now. So in these tactile robots, if you look at collision speeds and collision masses, so on the pendulum, the question is obviously if it's black, didn't detect the collision, if it's white, it detects the collision, right? So I think it's very clear that in human-robot interaction, safety, this should be a very important thing to be able to do if you have a robot collaborating with humans, right? And especially it's important if you do manipulation. Okay, same thing with the constraint forces from the TS 15066. So we just recently published all that work at the International Conference on Safety in Robotics and kind of compared on these various benchmarks and really are releasing at the moment a set of full benchmarks in order to compare all these robotic systems, and there's more and more coming. We see new robots coming everywhere, which is amazing, and I think it would be so cool to really be objectively able to compare them, obviously. Right, then next level. What comes now? And what is also part of this whole tactile robots revolution? It's really the ability to learn, and not to just look at deep learning and think it's an amazing thing for robotics. No, it's not. It's an amazing thing for computer vision. It has transformed computer vision. But if you compare actually deep learning and really state-of-the-art actually reinforcement learning, deep reinforcement learning, with new kinds of algorithms that really kind of go to this next level of machine learning, which we call collective learning, really a marvelous thing happens. We actually can solve these things really with learning methods that are not only faster than standard deep learning by orders of magnitude, but they're actually able to learn these extremely difficult tasks without any prior knowledge, except for the fact, bring that key into the hole and the robot just learns within, I mean, it takes a few trials to learn that. No programming involved. And if you try standard deep learning, you do very hard, and I'm sorry that you cannot see it really well here, and you try really hard, we're not even able to train the system for weeks to be able to converge to the specific goal if we didn't give it boundaries that were so narrow that you essentially solve the task already by hand. So what do you see here? That's the cost function. You know, cost function, the lower the better. And on the left side, you see the cost function as 0.5, right? It converged. These new machine learning algorithms, that where this is, let's say the magic sauce is essentially, you've got concepts of neuromotor control of humans, you combine them with reinforcement learning or cost-based learning, and then you come up with these, you know, convergence of very, very fast trial iterations. So just takes 5 or 10 iterations. So that's a matter of 20 seconds, system is converging. If you take the deep learning end, you converge as well, and all the standard algorithms of reinforcement or deep reinforcement learning at the moment, problem is they all converge to not being able to do it. So we were really not able to essentially use standard deep learning to solve robot manipulation learning. So is it a surprise? I think for robotics it's not really a surprise. Why? Because interaction is not just a pipeline. And this is exactly now what we scale tremendously to what we call collective learning. So with this basic idea of having robots that are able to, you know, learn how to interact with the world, learn how to manipulate. Next question is, we are in an age of you know, 5G interconnected networks and so on. I hear 6G is coming. We have great interactions with Dresden here. So Munich and Dresden are working in a 6G Live project together. What happens if we now connect a lot of robots with each other and let them learn from each other in real time, basically? Can we even go beyond to what I just told you? Can we, in the limit, go to single-shot learning? So is it possible to, within an instant, to basically learn a task? Obviously, this has limits, but if you look at what we're doing here, the task was essentially that the robot in the beginning is supposed, you know, this one, is supposed to try to get the key into the hole. Obviously, it's a newborn robot. There's no idea what it's doing. Yeah? And now it's kind of asking its siblings who are sitting here in the cloud. So this is the digital twin being implemented that's kind of collecting the knowledge from all the robots. And by the way, every robot has a different key, a different gripper, and a different location. So it's never the same task. And all the robots are collecting this information at the same time and learning something that says, you know, if it's green, worked, if it's red, it didn't work. So obviously at some point, the red stops growing, and at some point, green just takes over. So optimal robustness and solution of the task. An interesting thing is, just within a matter of seconds, essentially, you can see how the first robots are still not working, so they are not successful in doing the task, but then the first ones, just within a matter of 1 or 2 iterations, are successful. So you can see after, I think, iteration 2 or 3, the first robot really being able to insert the key into the hole in basically out of scratch. And then, next question, can the robot in the front insert the key into the tilted platform, so a program that has not been taught on the other side, and with a different key than all the other robots have been doing, and can this be transferred? And the transfer should be only geometrically. And the answer is yes, the robot can do it. So the robot takes the motor control program it learned from all the other siblings, inserts it into the hole, and is able to do it immediately. And then obviously you could still improve. Okay, so how can we bring this even further? We talk about sim to real transfer, right? So can we actually bring this now to manipulation processes that are learning in digital worlds? So these are physics simulators. And we always hear that from physics to reality we can do the transfer. Well, to be honest, it has quite limits because, I mean, simulating the reality, come on, let's face it, it's not just possible. We all know that. So processes are complex, but there are certain interesting abstractions we can do. So we need to find the right abstraction to be able to, simulate the same processes, key into the hole in the digital world. And can we do this with a transfer to reality? So where are we there? What I show you here is still unpublished stuff, but I think it's interesting. On the left side, you see basically an arm trying to learn the right impedances to be able to grasp a door handle that is, 5 centimeters unknown position. So what is the right impedance to glide into the contact? So the robot does not yet know exactly where the handle is. And it learns the right compliance in the wrist and the forces and so on to be able to do this. Interestingly, if you do this in a simulated world, which you can run anywhere, so let's say overnight or just before the other robot is doing something, and then you transfer it into the reality, actually the recent results show that in reality, we see now here the humanoid Garmi in Garmisch-Partenkirchen trying to open doors in our apartment there, and the robot is now using exactly the program it learned in digital world, in the physics simulator, use it in reality, and then immediately it's able to open the door. So I think this is showing as a first step that we can really do the extension of the robot machine learning into the physical world and not vice versa. So the initial step has to come from reality, then get it back to the simulator, and then use this kind of physics grounded or reality grounded simulator to then leverage all these huge data that you can use there. Why is this important? Because now we can really think about aspects that have not been possible for robots. We talk about safety, yes, that's one thing. We talk about cobots, okay, that's no safety fences. But if you want to do teleoperation with force feedback for the elderly, for example, something in the pandemics would have been a major contribution of robotics to this crisis we have seen. So think about the lockdown of the care homes, right? Think about if you could just, as a private doctor, enter into a robotic avatar, use that force feedback channel to then do all the standard diagnostics that a typical doctor does with your patient at hand. So this would have been a tremendous change. So I think this interaction of humans and machines, not only over physical spaces, digital space, but actually over, you could say, space and time to some extent, is I think something we can really leverage over the next years. So this is something that has become reality and really can be used in the real world. And what is also, I think, super interesting is that these kind of things really bring automatica to the next level. So yesterday we had Minister President Söder here with us. He was opening the high-tech summit of Munich I. He was wandering around at automatica, and I think he was quite amazed what we as a community are doing. So this, robotics is not anymore only industry, it's coming into the real space, into our real world, and this brings all of us together to kind of, from basic research to translation and being able to do these things in the real world, not only in industry. I think that's super important for all of us, but I think the health sector and others can now tremendously benefit from that. Last but not least, this brings me to my last slide. This has been a work of many people, many contributors, and I would like to thank all of them. And I know I probably left out hundreds of them, and I'm so sorry for that, but I want you to know that you're all appreciated and acknowledged. Thanks for your attention. Thanks for being in Automatica. I think we have a great fair here. It's a great platform. It's so nice to see all of you again. Thanks so much, and take care. Thanks.